Hi, this is John Whitaker, and this is our first video for the Mathematical Analysis 2 course. And I want to start by reviewing some of the things that we've seen in the first Mathematical Analysis class that we'll be using fairly soon for this class. First thing that I want to start off with is recalling a definition. So the first definition we want to look at is that of a metric space. So what's a metric space? Let's recall. A metric space, or a set, X whose elements we shall call points, is said to be a metric space if with any 2 points P and Q of X okay, there is associated a real number D of PQ called the distance from P to Q such that 3 things are satisfied. The first thing is that the distance from P to Q is always greater than 0 if P is different from Q and the distance from P to P is 0. That's the first thing. The second criterion is that the distance between P and Q equals to the distance between Q and P. And the third criterion that must be satisfied by this D is that the distance between P and Q is going to be less than or equal to the distance between P and R plus the distance between R and Q, and this is for any R element of X. Okay, so that's the definition of a metric, and we've seen examples of this in the past. Before I get to the examples, let me back here. And make this comment. We call such a function d of PQ the distance function. So as examples, things that we've seen before is that if x is the real numbers, then the distance between, let's say, P and Q is given by the absolute value of P minus Q, is the usual metric. On R. We also saw one that was an extension of this, distance function. That is another example. If we have x being equal to rk, that's the set of all k tuples whose each entry is a real number, with, let's say, P being equal to P1, P2, up to Pk, and Q being equal to Q1, Q2, all the way up to Qk. Then, the distance between P and Q is given by the sum of P1 minus Q1 to be squared, as I runs from 1 to k, and all that square rooted, raised to the 1/2 power. And this is called the usual metric on RK. So we had talked about metric spaces in the previous class, and that's the definition along with 2 examples with R and RK, and we'll be looking at those type of metric spaces in Chapter 5, which is really the first starting content material for the class after we get through this background Macaulay material. Also, as a review, we'd like to look at some topological definitions that we've seen before. This is from Chapter 2 of our text. And here's the definition. It says, let X be a metric space then we're going to have the following definitions. It says a neighborhood of P is a set, and that set is denoted by n sub r of P, which is a subset of X, the set for which we're having the metric, consisting of all points Q such that the distance between P and Q is less than R for some R. This R is given to us, or we're picking it. For some R greater than 0. This R, the number R, is called the radius of the neighborhood. So that was one definition. A secondary definition is that of a limit point. So, a point P is the limit point of some set E of X if every neighborhood of P contains a point Q that's from E where Q is not equal to E. Let us now look at some examples. Okay. This example, consider R with the usual metric that's the absolute value function, and then we'll say d of, I'll say xy equaling to the absolute value of the difference between x and y. Then, so we have two examples here that I'll do. The first is that the neighborhood of radius 1/2 centered at -1, what that equals to, it equals to the open interval from -3/2 to -1/2. And so pictorially what this is, if we think about -1 being the center of our neighborhood, then what we're doing is we're taking all the points in R, whose distance from -1 is less than 1/2. So that means we can go half a unit to the right, and then we'd be at -1/2, and half a unit to the left, and that puts us at -3/2. So we're talking about all the numbers in between -3/2 and -1. If we look at another example, in terms of getting for limit points, if we let E, in our same setup where we're talking about R with the usual metric on it, if we let E be equal to the set that looks like 1/n, the sequence 1/n is n runs from 1 to infinity, union with the interval from, let's say, 2 to 3, okay, then 0 is a limit point, even though it's not in the set E. let's say 2.5 is a limit point. Of E, but 1 is not a limit point. One is not a limit point. We look at this example pictorially. Here's what we're having. So we're looking from 2 to 3 in this manner. We're not including 2, but we are including, we're not including 3, but we are including 2. And then here's 0. And then when I look at the 1 over n part of E, the first number we get out when n is equal to 1 is 1. And then we get out 1/2, then 1/3, and so forth. And we keep getting dots closer and closer together, and they're getting closer and closer to 0. And so that's why 0 is a limit point, is because anytime I take any neighborhood, that means some little ball, if you will, that has that includes 0. So it means that part of the ball is to the right of 0, part of the ball is to the left. Because we're getting some part to the right, we're going to get elements from E that are within that ball that we make, that neighborhood that we make. The neighborhood and ball is the same thing, as you say. We said that 2.5 is also a limit point, let's say, because anytime I make some little neighborhood about 2.5, it definitely is going to include things from E that aren't 2.5 in any neighborhood I make about it, because I'm going to have points to the left and points to the right. Okay. Okay. And then I said that 1 is not a limit point. That's because I can make this neighborhood, one whose distance or whose radius is less than, let's say, 1/2. And within that neighborhood, the only point from E in that neighborhood is 1. But to be a limit point, we've got to have a point other than 1 for 1 to be a limit point from E within that neighborhood. We don't. So that's some examples. The next thing we want to look at is a definition about the limit of a function. So here is a definition. This is recall. We let x and y be metric spaces. Suppose E is a subset, I'll write it this way, of X. F maps E into Y, and P is a limit point of E. We write f of P goes to Q, I'm sorry, not f of P, but f of X goes to Q for X going to P if if there exists a point Q in Y such that, or with the following property, that is, for each epsilon greater than 0, there exists, remember that's our symbol for there exists, a delta, a positive number, delta greater than 0, such that for all x element of E with the distance between x and p being less than delta, then the distance between f of x, the output values, and q is less than epsilon, and this distance has to be greater than 0. So we're not interested what happens, I'm sorry, this has to be greater than 0 in the state. So for all x in E with the distance between x and p being less than delta but yet greater than 0, that means that we want x to be really close to p, but this part right here says we don't want x to be equal to p. Then the output values for the function, their distance from q are really close to q, really small that distance is, less than epsilon, whatever epsilon has to be. And in this case, we say that the limit as x goes to p of f of x equals to q. Okay, let's look at an example. Let's look at the limit as x goes to 3 of minus 2x plus 5, and show that that's equal to minus 1. So what we're thinking of here, in parenthetical expression here, f of x, really it goes from R into R, and I'm thinking about on R having both sides, having the Euclidean or the usual metric. And f is defined by f of x is equal to minus 2x plus 5. Okay? And we're having x going to 3, so 3 is our p, and our q, which is in this brain space, is minus 1. Okay. So let's see here. How do we prove this? The way we prove it is that we say, well, let epsilon be greater than 0 be given. What we're looking for is we need a delta bigger than 0 such that for all x in R, that's the first step, with 0 is less than, well, the distance on R, which we're saying is the usual metric, that's x minus, and here p, so it's 3. That's got to be bigger than 0, yet less than delta. Then the absolute value of f of x minus what we think q is, so that's minus 1, will be less than epsilon. That is, we want the absolute value of f of x, well that's minus 2x plus 5 minus a minus 1 to be less than epsilon. That is, we want, here this would be minus 2x plus 6 to be less than epsilon. So what we want is, if we pull out a minus 2, we have minus 2 times x minus 3 to be less than epsilon. I can break up the absolute value of multiplication into the multiplication of the absolute value. So we want the absolute value of minus 2 times the absolute value of x minus 3 to be less than epsilon. So we want x minus 3 inside absolute values to be less than epsilon divided by the absolute value of minus 2. But that's just epsilon over 2. So this x minus 3 inside absolute value is what we get to control. So what we do here is we let delta equal to epsilon over 2. And then everything works out. Let's look for that. Next, we want to list a fact. We suppose E is a subset of X, which is a metric space. P is a limit point. B, F, and G are complex functions on E, and the limit as x goes to P of f of x equals to A, and the limit as x goes to P of g of x equals to B. Then then the conclusion of this fact, we have three results. The first result, these are algebraic properties of limits, that the limit as x goes to P of f plus g acting on x is equal to a plus b. The second one is that the limit as x goes to p of f times g acting on x is equal to a times b. And c is that the limit as x goes to p of f divided by g acting on x is equal to a over b, and that's provided b is different from 0. Okay, so this is a fact that we've seen before, and essentially this fact is saying that if you add two functions whose limit exists at p, the result of the limit of those two functions added together is the addition of the limits. Likewise, the limit of a multiplication is the multiplication between limits, and the limit of a division is the division between limits, provided that the limit of the bottom function isn't 0. That's something we've proven before. Another fact we want to look at is suppose, it's a fact, suppose x and y are metric spaces I shouldn't say this is a fact, this is a definition. Sorry. So definition. So we're supposing x and y are metric spaces. And E is a subset of x. P is an element of A. So not necessarily a limit point, but an element of A. And F maps E into Y. Then F is said to be continuous. At P, if for each epsilon greater than 0, there exists a delta bigger than 0, such that for all x element of E, this x is an element of E, which is an element of big X. So let's make this a little x. With the metric in the big set X of xp being less than delta, then the distance in the set Y between f of x and f of p, okay, will be less than epsilon. Less than epsilon. Okay, what this is saying is that for continuity, first of all, you have to be, we're talking about continuity point, you have to be a point, this point should be an E, I made a mistake here, not A. Point in point in E, that's a big mistake on my part. You have to be a point in the domain space, and to be continuous at that point, what has to happen is that no matter what distance you give me, epsilon, there's another distance, we call it delta, such that if you look at values in E that are very close to P, in delta units, then the output values of the function of those x values will be very close to, within epsilon units, of the output value at P. Right. That's what it says. So there was a correction there that it shouldn't be P element of X, it should be P element of E. We'll do an example next. So as an example, we'll show that f of x equaling to 3x plus 7 is continuous at x equal to 2, where E is equal to R, and the metric on X, or on R, is our usual metric. So that's X minus Y. And the metric on Y, I'll say of W and Z, is the same. It's the absolute value of W minus V. So here we're thinking as F goes from E, or from R, into R. So show it's continuous. Well, how do I show it's continuous? Well, we start off with proof. We let epsilon be greater than 0 be given. We need a delta bigger than 0 such that for all x element of E, or R in this case, with, well, the metric here, well, that's just absolute value, x minus, and here we have to write down what P was. That's 2. Whenever that's less than delta, then the metric in Y, the output space, well, that's just absolute value again. So here we have f of x minus f of 2 will be less than epsilon. So that's what we want to have happen. So we want the absolute value of f of x, but f of x in this case is 3x plus 7 minus, it's f of 2, but f of 2 is going to be 6 plus 7, it's going to be 13. We want that to be less than epsilon. So we try to rewrite what we want in terms of what we can control with here. And so that means we want absolute value of 3x, this would be minus 6 to be less than epsilon. So we want, I factor out of 3, the absolute value of 3 times x minus 2 to be less than epsilon. That means we want 3 times absolute value of x minus 2 to be less than epsilon. I can control how close x is to 2, so that means we want x minus 2 to be less than epsilon, so we let delta be equal to epsilon, I'm sorry, this should have been epsilon over 3. So we let delta b equal to epsilon over 3. That's what we need. We need that delta. So that's the delta that works. Next, I want to list a fact. Here's what it says. It says, let x and y be metric spaces. X and y are metric spaces. And E be a subset of X. Let F be a function that goes from E into Y, and P be a limit point of E and P be an element of E. Then F is continuous at P if and only if the limit as x goes to P of f of x equals to f of P. So this is a fact that we had last class, the Math Analysis 1, that we've proven, and I'm just reminding you of it now. That's something that's going to come into play for us this term. We'll look at an example. We'll say let F go from 1 close to interval from 1 to 7 into R. And we can think of this being our X and this being our Y, or this being our E of X, which is the real numbers. Okay. Be defined by f of x is equal to 3x squared minus 5. I'm sorry, I didn't want to do this example yet. Let me back up. Please forgive me. Instead, what I wanted to do is really start the content for the class. This was an example of our first concept that we're going to do. And that is, we're starting now chapter 5, after having this background. And it has to do with differentiation. And what we're going to do is we will mostly consider functions defined on intervals. And what we mean by intervals is the closed interval from A to B of real numbers or segments. And that's the open intervals from A to B of real numbers. Okay, and we're going to give the definition of what it means to be the derivative of a function at a point. So here's the definition. So it says, let F be defined and real value on A to B. Then it says for any X element of A to B, form the quotient. This is sometimes called a quotient function. Phi of t, and it's given by f of t minus f of x all over t minus x. And this is for A being less than T, being less than B, and also we have the restriction that T is different from X. And define f prime of x to be equal to the limit as t goes to x of phi of t, okay, provided this limit exists. Then f prime of x is called f prime of x is called the derivative of f at x. And that's our definition. I'd like to do that example started to illustrate this definition. So as a quick example, here we'll let f go from 1 to 7 into R, be defined by f of x is equal to 3x squared minus 5. Okay. Then f prime of 2 will be equal to 12. We'll prove this. That's the last thing we'll do today. So here's the proof. Okay. Well, f prime of 2, if it exists, is equal to the limit as t goes to our x in our definition, but x here is 2. It's f of t minus, it's f of x, but here f of x is going to be f of 2 all over t minus 2. This is going to be equal to the limit as t goes to 2 of f of t, in this case, is going to be 3t squared minus 5 minus, and then f of 2 is what I get out when I stick in 2 into x, into f of x. And so that's going to be 4 times 3 is 12, minus 5, that's 7. All over t minus 2. Here, we end up getting the limit as t goes to 2 of 3t squared minus 12 all over t minus 2. This is going to be equal to the limit as t goes to 2. I factor out a 3, I'm left with 3 times t squared minus 4 over t minus 2. And that's equal to a limit as t goes to 2 of 3 times, here this is going to be t minus 2 times 2 plus 2 all over t minus 2. And that's going to be equal to the limit as t goes to 2, canceling out the t minus 2, of 3 times t plus 2. Okay. Okay. That says, so f prime of 2 is equal to the limit as t goes to 2 of 3t plus 6. And the claim is that this limit as t goes to 2 of 3t plus 6 equals to 12. Okay, and I'm using the usual metric on R. And so here, to prove this limit is equal to 12, what we'll do is we'll let epsilon be greater than 0 be given. So here I'm doing the proof of claim. Okay. What do we need? We need a delta bigger than 0 such that for all, here it would be t, element of R with 0 less than the absolute value of t minus 2 less than delta, then the absolute value of 3t plus 6 minus 12 is less than epsilon. So, we want the absolute value of 3t minus 6 to be less than epsilon. We want the absolute value of 3 times t minus 2 to be less than epsilon. So we want 3 times the absolute value of t minus 2 to be less than epsilon. So we want t minus 2 inside absolute values to be less than epsilon over 3. So we let delta be equal to epsilon over 3. And that's the end of the proof of the claim. And so f prime of 2, the derivative of our function of 2, does indeed equal to 12. That's all that I have for our first lecture. Thank you very much.